as a function from the system's input to the system state. That's a surjective map. And so last day we defined for controllability. So let's just do a brief recap of where we are. And this is all in lecture note 17. For controllability, we defined the controllability map, LC, and this for linear time varying systems. So it's a function of, it takes the input function u between some point t0 and some time point t1, and it gives a state. All right, so it's just that portion of the state transition function which maps the input to the state. Okay, so that's what we defined as the controllability map. Let's just write it here. Controllability map. And so we want for controllability, or let's use the term which we defined last day, CC, which means complete controllability. Is for complete controllability, we want that LC is surjective, or written differently, the range of LC is equal to Rn. All right, so what's, as we derive this, remember how we derived it. We wrote out what the state transition function is. We moved that component of the state transition function, which depends on the initial state, over to the left-hand side of the equation. And so what we had on the left-hand side of the equation was some x at time t1 minus phi at time t1, given that we started at time t0 times x0. So on the left-hand side, we have everything that represents the state, or states x0 and x1. And on the right-hand side, we're left with kind of the core of what's important, which is the map that takes the input to that state, or to that linear combination of states. Okay, so that's where we got to last day. And similarly, for the observability system, so the observability map, we did the same thing, starting from the point of defining observability very intuitively as the ability to take the input function over a period t0 to t1, record the output function over that same period t0 to t1, and from those two functions, the ability to uniquely determine what the initial state of the system was. So then we related that to, almost immediately, to the injectivity of the system's response map. And then last day, we determined, like, what is at the heart of that? And so we rewrote the response function, again collecting like terms on the left-hand side, as in terms of what we defined as the observability map. And that's a map from the initial state to the output, or something that looks like an output function. And so it's, and I'm going to write it using our dot to represent the argument that this is a computed over a time horizon, t0 to t1. Okay, so whereas LC is a map that takes input functions to the state space Rn, LO is a map which takes Rn in the form of the initial state to output functions over the interval t0 to t1. Okay, and that's and that just is that component which really involves the initial state. Okay, and so then injectivity of the response function is the same as injectivity of this map LO. So complete observability or CO happens when the null space of this map LO is equal to just the zero vector. So we ended last day by saying, well, these are mathematical tests, but you know, they're kind of hard mathematical tests. They're not hard, but awkward sometimes. So we're testing the surjectivity of this map, which is an integral. Or we're testing the injectivity of this map, which gives us a function over time. So could we turn these into matrix rank tests? And that's where we were getting to last day. And we can do that by recalling the definition of an adjoint. So in one of the exercises last day, we computed the adjoint of the controllability map. So can we turn these tests into, and I'm going to say simpler. By simpler, I mean, you know, it's typically a computational algorithm that, you know, is canonical, that we can always sort of do in the same way, into simpler matrix rank tests. And the answer is yes. And we do that by invoking the adjoint of both maps, and then using a very useful lemma, which is where we ended last day. Okay, so in particular last day, we computed the adjoint of this map LC. So let's put our diagram, again, our canonical diagram of linear maps from a domain to a codomain. LC is mapping U to Rn. LC is a linear map. LC star, its adjoint, defined through the inner product, as we recall, is mapping Rn back to U. And so in one of our exercises last day, we computed LC star. So what is LC star? LC star's domain is Rn, so it takes a vector x, and it's going to give us a function u from t0 to t1. All right, so this is what we computed last day. We actually used it as an exercise. Instead of calling it LC star, we called it A star, but we did that exercise, and you see it there in lecture notes, 17. And so we computed this. You can find, I can look for you, but I think you can probably find it quite easily. And so what is that? That just is how we define the adjoint of the map LC. Similarly, we've got the map LO, and you can go ahead and compute. So we did this in class, but as an exercise, you can go ahead and compute the adjoint of the map LO. So let's again recall our spaces here. We have LO, it's mapping Rn over to the function space Y. Star is coming back, so the adjoint of the map LO goes from the function space Y back to Rn. And you can do this, you can verify this. In fact, I'll put it as a question on the homework 8 that I'm going to post tonight. That the adjoint of the observability map is, so what does it do? It takes functions Y, and it maps it back to states in Rn using the following map. Okay, so I'm going to say exercise, and I'm actually going to put this on homework 8. Okay, so you can go ahead and do that adjoint calculation. Okay, so so we've got the adjoints of those, and where we ended up last day was this lemma on page 8. So, or this proposition we called it, or a very useful proposition. And that had 4 parts to it, although parts 3 and 4 are really just a repeat of parts A and of parts 1 and 2. So if you have a linear map A between two vector spaces U and V, the null space of A star is equal to the null space of A star. The range of A star is equal to the range of A. And then similarly, we can see this just by flipping A and A star. The null space of A star A is the null space of A. and the range of A star A is equal to the range of A star. Now this is a lemma or proposition that we've seen before. We treated it partially back when we were doing singular value, when we were presenting singular value decomposition. And kind of the new pieces that we've put in now is when we look at this decomposition of our vector spaces, and I'm just going to call this vector space the generic U, and this vector space the generic V, we can decompose those vector spaces into a direct sum orthogonal decomposition of these components. Okay, so that's my space U. So this is the 0 vector in U. This is the 0 vector in V. A is a linear map. A star is its adjoint. Going back. And so these component spaces. So this is the null space of A. This is the range of A star. This is the null space of A star and the range of A. And in one of the propositions that we proved last day, we showed that these two spaces are orthogonal to each other, and we also proved that, that their direct sum is equal to the vector space U, the domain. Similarly for the spaces over to V. All right, so that's the structure that, you know, we're always thinking about this sort of generic structure, but when we have a linear map A and its adjoint, we can do this composition, and we're going to be thinking about that. So last day we proved the first one. Actually, the proof last day when we were going through it, what I said first was true, as thanks to Kate for pointing that out at the end of last day's lecture, is that you can just draw equivalences between every step of that proof, and you can go through the notes and see why that's true. But basically, when we're trying to prove that two sets are equal to each other, we have to show that this set is contained in this set, and this set is contained in that set. So our basic strategy is to take a vector in the null space of A star, and then show that it's in the null space of A star, and then take a vector in the null space of A star and show that it's also contained in the null space of A star. Okay, so we did that last day. Yeah.
So if, are you saying that there's like new information that for the proof of this thing is a subset of that, and that thing is a subset of that, like, that there is equivalences at every step?
There is equivalences at every step.
Even though we choose a certain...
Yeah, even though so at the end of last day's class I was saying, well, we're choosing a certain V, vector V, but the reverse of that holds too. So go back and check that in fact you can, the proof that I have in the notes is correct, that the equivalences occur at every step. So there's one step where we choose a particular V equal to V1, but the reverse of that works too. So you can add a double equivalence in that step too. Okay, so let's prove 2. Once we've proven 2, we've also proven 4, and so now that we've proven 1, we've also proven 3, right? Because you can just replace A and A star in those. All right, so the proof of this, it's a nice little proof, is we're going to start with vector V. So let's take a vector V which belongs in the range of A. So a vector V in the range of A. And so what do we know about that? We're going to try to show it's also in the range of A star. Okay, so that means that V is equal to A times, or A operating on U for some U in the domain. And we also know that U in the domain, by the fact that we can decompose the domain as the direct sum of these two spaces, we know that U is equal to U1 plus the fact that it's in the domain tells us that it's equal to U1 plus U2, where U1 belongs to the range of A star, and U2 belongs to the null space of A. Okay, so then if we look at AU, V is equal to AU, which is A U1 plus U2. Sorry, I'm going a little bit further on this side. Can you see?
Yeah.
Yeah, okay. So that's AU1 plus AU2. But U2 is in the null space of A, so this goes to 0. That component's always zeroed by the fact that U2 is in the null space of A. So that's equal to AU1. So V equals AU1. But U1 is in the range of A star, right? So that means that I can write U1 as some A star times some other vector Z, where Z is a vector in, it's coming from the space V, just by the fact that U1 is in the range of A star. Okay, so that tells us that, you know, if we started out in the range of A, we're also, that vector V is also in the range of A star, because I can write it as A star Z for some vector Z in the space V. Okay, so that's a useful trick. We haven't really seen that before, and that comes, or we haven't really seen this technique before directly in this class, but it comes from the ability to do that decomposition. Yeah.
In terms of proofs, is for Z element of V the same thing as for all Z element of V?
No, it says that for, let's write it the same way we did here, it means for some Z. So when you say that something is in the range of something else, it means that it can be written as that, so if it's in the range of A, it can be written as A times some vector, right? That's what it means to be in the range. So it's the same thing here, we'll just write that for some Z in V. That's all I know here. Okay, so that tells me that the range of A, so what I've just done here is telling me that the range of A is a subset of the range of A star. Now the other direction is the easier direction. If you have something that's in the range of A star, so choose some vector x which is in the range of A star, it's automatically in the range of A because A pre-multiplies A star. So that direction is kind of the obvious from writing it out direction. But range of A star is always a subset of the range of A. Right? Because a vector that's in that range, just write it as some vector, and then it's A times A star times some vector, so it's in the range of A. All right, so we have those, now we have those two sets are equal to each other. So double containment proves equality of sets. And then 3 and 4 follow directly from the previous. All right, now why is this important right now? Why are we talking about this right now? Well, now let's go back to this question about turning these tests into matrix rank tests. And let's look at the structure of the, in the case of, say, the controllability map, we've got that, we want the controllability map to be surjective, and I want to turn that into a matrix rank test. Now, let's take a look at applying the one that we've just proven, the part 2 of the proposition, to the test for controllability. So, I don't really want to erase what I just did, so let's just, but I'd like to keep this on the board. So, and I'd also like to, I've got so much stuff that I want to keep on the board. So, let's see, maybe I can just sort of complete it right down here. All right, so I've got LC, I've got LC star, but I know that from what we've just chosen, so from part 2 of the proposition, I know that the range of LC is equal to the range of LC star. Well, why is that interesting to me? Let's actually just write out what the map LC star is. Okay, so LC is a map from U to Rn. LC star is a map from Rn to back to U. So LC star, what's that a map from? So they're composing those two maps, right? Rn to Rn, yeah. You're taking, so look where you're starting. You're starting in Rn. You're applying LC star, and then you're applying LC. So you start in Rn, you go through this, you come back to Rn. All right, so it's a map from Rn to Rn. Any map between finite dimensional vectors, any linear map between finite dimensional vector spaces can be represented as matrix multiplication, right? Good. And so we know we can represent it as a matrix. What is that matrix? Let's work it out. We know what LC is. We know what LC star is. So it says take a vector, apply LC star to it. Okay, so I took a vector x in Rn. I applied LC star, and I got this vector, which is a function. But then I take that function, and now I apply LC to it. All right, here's LC. So where I see the U here, I'm going to put in this function here. That's what LC star is. You first map through LC star, take a vector x, map it through LC star, take the result, which is a function, plug it in here, and map through LC. All right, so LC star of x is equal to, so I'm going to start with I'm going to start with LC star, but I'm going to take that function and plug it in where I see U here.
Can you do the color coding thing?
What's the color coding thing?
Which is where you so you're doing a bunch of layered substitutions on top of each other, and it's kind of easy to follow what's happening.
Okay, so we're taking,
sometimes I like to draw numbers, but you can also underline different colors.
yeah, okay, so we're taking LC star x here, and I'm plugging this in to U here. Okay, so I'm taking LC star x, and then I'm applying LC to it. So it means I'm taking this function here, and I'm applying LC. Well, LC takes a function. So wherever I see U as a function, I'm going to plug in this function here. So let's keep the color coding. Let's write the LC operation in black. So that's just this piece here. The integral from T0 to T1 of phi of T1 tau, B at tau. Now, wherever I saw U of tau, I'm going to plug in this function here. So it's a function of wherever I see the dot, I put in tau. B star of tau, phi star of T1 comma tau, x, d tau. X is just a vector, so I'm going to bring it outside that integral. Okay, so now we have something that is, in fact, an n by n matrix. This is an n by n matrix. Entries may be time varying, or are in general, well, they're dependent on T0 and T1 once you've done that integration. But it's an n by n matrix times a vector x. Okay, so now surjectivity, what does it mean for an n by n matrix to be surjective? It just means it's full rank, right? So it means that that n by n matrix has rank n. So the controllability of this system, and I'm dropping something here, I dropped something, you should have corrected me, because I told you it was important from the beginning, but the controllability, we have to be careful, it's over a time interval. So complete controllability, let me correct this one too, complete observability. All right, so these functions depend on T0 to T1. So does this matrix, right? It's the integral of this, this matrix product from T0 to T1. Yeah.
So why would a system, oh, never mind, I thought of one.
Okay, yeah, so it's just now we've turned like testing the search activity of a map to testing the rank of a matrix, right? So let's write our concluding sentence over here. Which of these do I want to keep for observability? Well, I'll rewrite it. No, which one? Okay, I'll rewrite it. But I'm going to keep this diagram up there. It's useful to have these diagrams in mind. I always draw these diagrams when I'm thinking about these maps, and in particular this question of composing maps. Because it is confusing when you're composing maps, so just be careful about how you're doing it. I always rederive it. I rederived it like half an hour ago just to make sure that I was doing it correctly. Yes?
Why do we, so that we better remember, why do we care so much about it being on a time interval? Like, what if we didn't write that? Like,
well, if you didn't write it, you may, you would be missing a key part of it, because for time-varying systems, it could be completely controllable from time 0, so you start at time 0, but it's time 0 to time 10 seconds. But if you only go up to 2 seconds, it may not be controllable. So because, if you see this here, this is an n-by-n matrix, but as you increase time, you're giving it more opportunity to have full rank. So as you integrate this integrand here, this product of matrices which depends on time, as you integrate that further and further, you're only giving it more opportunity to increase the rank. And I'm going to explain that in a second. So something that's controllable over a shorter time, and something that's controllable over a longer time interval may not be controllable over a shorter time interval. But if it's controllable over a longer time interval, it will certainly be controllable for longer than that time interval. Right? So that's an interesting point that you raised.
So I don't know if this question makes sense, but somehow what we are doing here is consider some system whose zero input solution is phi star. In some sense, we are putting that as the input, the state of that system as the input here, and our proof technique shows that somehow gives us some relationship between the range.
So you're just looking at this, right?
Yeah. What's happening here is what I mean. Is there some intuition behind what's like? I see the math, but is there something deeper happening there?
I think the intuition is all in this statement here. I find it hard to gain, and so the intuition here is that we have an input, and how the input interacts with the dynamics of the system, well, through the dynamics of the system is really just captured in this map here. So the ability to be able to reach different states in the system, depends on the ability to, using that input, mapping it through B and then phi, to be able to get on the left-hand side, any possible state in Rn. So it's really about, what dimension, can you reach the full space Rn through this map here? I don't really have good intuition. So what I know is really what we've proven. That, when we look at these maps, when we look at that composition of these two maps, the range of that, and we can gather intuition from the proof, the range of that is really the same as the range of LC. So it gives us a convenient way of really testing this condition here, but this is the one that I would lean to for the intuition. And so this map here is, so now what we're doing is we're turning this problem around, and we're saying that surge activity, well, we're not turning the problem around, but we're going one step further, and we're saying that the system is completely controllable on this interval t0 to t1 if we've got that the range of this map, LC star, is equal to Rn, which is the same as saying that that LC star has rank n, because it's an n-by-n matrix. And in fact, all of these, as we've been saying from the beginning, these are all double implies. All right, so when we're talking about complete controllability, that implies that implies that.
So for an LTI system, then it would always be controllable or observable if it was at like any time interval.
Yeah, and we'll talk about that in a few minutes. Yes.
So what do you mean by complete? Complete control?
Yeah, so we'll talk about that in a few minutes too. So I introduced this word complete without, or the C before the C, without really saying anything about it. And I'll just say very quickly, and we'll come back to this later, that you can have a subspace of Rn that's controllable, but the whole space isn't controllable. And what that means is you can't get from any initial state to any final state for some systems, but you may be able to get from any initial state in some subspace of Rn to another state in that subspace of Rn. And it turns out that the span of the columns of LC star gives you what's called the controllable subspace. So you can have partial controllability, which is how this terminology complete controllability comes in. It means that you can get from anywhere in Rn to any. It means that the whole of Rn is controllable, not just some subspace of it. All right, good. So we've got now a matrix rank test, and we define this system. We define this matrix. It has a special name. We call it WC. It's a function of this time interval through the integral t0 to t1. So I'm just going to rewrite this matrix here. So it's phi at time t1 comma tau, b at tau, b star of tau, b star of tau, or t1 tau, d tau. Remember, the star means the complex conjugate transpose. So if it's a real matrix, these are just the transposes. But in general, if they're complex, then that's the complex conjugate transpose. Okay, so that's an n by n matrix. And it's called the Controllability Grammian. Okay, this is always, in general, this matrix is always positive semi-definite. Meaning that for all t, between t0 to t1, its eigenvalues are always either 0 or positive. So it's always positive semi-definite, but for complete controllability, you need it to be positive definite. It's also symmetric. And these are very easy to test. So, test by looking at X transpose WCX, or taking the transpose. So for symmetry, you just take the transpose of the matrix, or the complex conjugate transpose. You see that it's the same thing. For positive semi-definite, you just test for any X if X transpose WCX is greater than or equal to 0, and you can. I guess I should say X star, because now we're in complex conjugate transpose. You want to make sure that that's a positive semi-definite. It's greater than or equal to 0 for any X. Okay. So when I say that, coming back to that point about a system may be controllable over a longer time interval, but not a shorter time interval, now it starts to make sense. Because if this matrix is always positive semi-definite, then if you integrate for more time, you can only be adding more positivity to it. You may not get more positivity, but you can't lose any positivity from it as you integrate over time. So it may be, so I'm just going to make a remark here to remind ourselves. Remark. The interval t0 to t1 is important. A system, and remember last day we talked about controllability being fully represented by the AB matrices of the system. A system AB may be controllable over, and just so we can see it in a diagram, it may be controllable over t0 to t1, like that longer time interval, but not over, say, t0 to some t1, let's call it t1 prime here, some intermediate time point. question.
So this is saying you couldn't have the reverse thing, like have it be controllable over a short
Yeah.
time and not over a long.
No, you can have the reverse. So if it's controllable over the short time interval, then by adding more time, you're only increasing the positivity of it. So if you're controllable over the shorter time interval, then you'll be controllable over any time interval beyond that.
Right.
And one way to see that intuitively is to go back to the statement of what it means to be controllable. If you're controllable over the shorter time interval, that means there exists an input to steer you from any initial state to any final state. So now you're automatically controllable over any longer time interval because you just have to, get to the final state and then kind of do what you need to do to stay at that final state. And so they're always, you can sort of show intuitively or through your, just the definition of how the control comes in, that there always exists an input. If you have an input that gets you from any x0 to any x1 over a shorter time interval, then you can construct an input from that input which will get you from any x0 to any x1 over the longer time interval. Yeah.
I'm wondering, do we have tools for analyzing whether a system is controllable subject to a certain cost, like the LQR formulation?
That's a good question, and I think the answer is yes. So the question is, do we have tools for evaluating controllability with respect to a certain cost? And so I think what you mean there is it may take because we're looking at these input spaces as vector spaces, right? So we're saying a system's controllable if there exists an input that steers you from any initial state to any final state. But the input space is a vector space, so any scaled version of that input is also a valid input. So it may be that you need a huge input to get you from some initial state to some final state over that time interval. So what if you put some kind of constraint or cost on the input? Do you still have controllability? So the answer is not necessarily, because you may, now you're taking your input space and you're trying to maybe restrict it some way, like through a U transpose RU kind of condition, or U is restricted to be, actuation limits, for example. Is it still controllable? And yes, I think there are, but the answer is that you're not necessarily going to have controllability over a restricted input space, just because you have controllability of the system through the vector space that we've defined from the start.
Shouldn't that be not true for any Bible stable system? Because Bible stable means that for any bounded input, you'll get a bounded output. So if you bounded your input, which you did if you put some constraint on the size of it, then your output is bounded, so it can't reach any arbitrary number in Rn.
That's true, but what are you saying what should not be true for a bistable system?
I'm saying that once you bound there shouldn't be a system where you bound the norm of the input and it's still completely controllable. And it's not if the system is Bible stable. If it's Bible stable and you bounded your input, right, then it can't be completely controllable because then you have some bound on the norm of your output.
No, I don't understand the connection here, because for a bistable system, it says that bounded inputs produce bounded outputs.
Yes.
Now, controllable just means that there exists an input to steer you from any initial state to any final
Yeah,
state.
but then for any final state, you can define the norm of that final state to be arbitrarily large. But then if the input is bounded, right, then the output itself is also bounded.
But you can still define a bounded input, right? The bound may be huge, but you can still define a bounded input.
That's true, but you can't be completely controllable because once you put some bound on the input, you actually also put some bound on the output for a Bible system.
So when we say we're controlling the system from any initial state to any final state, those initial state and that final state and that initial state are assumed to be finite. So a finite norm.
Fine, but then input is a finite norm.
Yeah.
Right? Then the range of outputs that I can get from it in a Bible system has to be finite as well, and then therefore it has to be bounded. And
But
therefore I
it-
can
but it's-
find some.
It still might be
outside
bounded,
of
but
that
the bound might be huge, right?
That's true. But,
Yeah.
but again, huge is still bounded in Rn for any finite huge number. If it's a Bible system and the input is bounded, the output is also bounded, hence it's not completely controllable.
No, I think there's a break in the logic here. So first of all, what we were talking about in the first question is that, you know, you define that bound. So you say, for bounded input, bounded output, it means there exists some bound k. But now we're saying, I want that bound k to be 4. I don't want it to go beyond 4. So now you're restricting yourself even more. But the relationship, we have to be careful now, the relationship between controllability and bounded input, bounded output stable is not, it's not so clear. There's a break there. We can continue this discussion. Yeah.
Somehow it becomes infinite case, so the bound becomes during the iterate, like your steering process is somehow kinds of can go to infinity.
Yeah, so, I mean, in all of how we define this, we've got, you know, controllability on some finite time interval is the ability to steer from, as soon as you define x0 and x1, you've got some, you know, you've got finite states. They may be really far away from each other, but they're finite. So you know, the input may be, you know, it may be huge, right? That's what we're saying here.
You said that if it's controllable over a shorter time period, then you can reach some whatever state you want to reach at a longer queue, and then you just stay at that point.
Well, actually what you do, it's like that, but what you actually do is you control yourself to where you need to be at time t1 prime, so that if you then turn off the input, you'll drift with 0 back down to t1. Okay, so that's kind of what we do. Okay, so let's continue. We've talked about controllability. We've turned it into a matrix rank test, and we define this controllability Grammian. Okay, so basically now the controllability is, let's just rewrite that as the, what do we call it? WC between time t0 to t1 has rank n. Okay, just to be explicit in terms of the controllability Grammian. We could do the same thing for observability. So now let's, for the sake of clarity, let's just go back to this part, the observability map. We want to turn the null space of this map here, being trivial, or only having the 0 vector, into another matrix rank test. And I think you can kind of see where we're going. So let's go back, let's use this part of the board for turning that null space test, the null space test of that map into a matrix rank condition. Okay, so suppose we go back to our very useful proposition and we look at proposition, or we look at the piece which is related to the null space. So let's take a look at the null space of L, where do I want to do here? I want to go, okay, so I'm going to look at the null space of LO star, LO. So first of all, if I compose, I first apply LO and then I apply LO star, what's the domain and the codomain of that map? Rn and Rn in both cases, right? Because you're starting off in Rn, you're first applying LO, and then you're applying LO star. So it's Rn to Rn. Any linear map between finite dimensional vector spaces can be represented as matrix multiplication. So let's find that specific matrix in terms of these LO star and LO. And so you will find out as you do this exercise on the homework. Actually, did we write down? Oh, I think I wrote it down and then erased it. But LO star, again, let's go back to our diagram. It takes a function, an output function between t0 and t1, and maps it to a vector in Rn. Okay, so it operates on a function, we'll call that y. and as you'll find as you derive this in the homework exercise, that's given by phi of tau t0 c star of tau y of tau d tau. Okay, so now let's look at the map LO star LO. So LO is over here. So we're first applying LO. We're taking a state x naught in Rn. We're applying LO to get this function. All right, so that's what we're doing here. We're getting that function y, and then we're operating on LO star. So let's use that same color coding we had before. We're going to take this piece here. We're operating on a vector x, x naught. So I'm going to write it like this. LO x naught is, I've just removed the brackets, but we know that's our operation. So that is, and then I'm going to apply LO star. Okay, so this piece here is this piece here. And let's write that, let's write like we did last time. Let's put LO star in black. So that's T0 to T1, phi of tau, T0, C star of tau. And then where we see the y here, we're plugging in this purple thing over here. And that's in under the integral tau, so it becomes C of tau, phi of tau, comma T0. And then I'm going to bring d tau, I'm going to bring the x0 outside like I did before. All right, so here we have our n by n matrix. This is an n by n matrix. And it's called the observability gradient. Okay, so we call that W sub 0. It's a function of the starting time and the final time through the limits of the integral of phi tau T0, C star of tau, C of tau, E of tau T0, D tau. Okay, and just like we called the previous one the observability or controllability Grammian, this is called the observability Grammian. It's an n by n matrix. It's always positive semi-definite. It's always symmetric. Same test is over here. When it's positive definite, the system is observable.
Just comparing this to the maths, I think there should be a star on the first beat. Just like the rest of the straight too.
Yeah, what, did I miss a star? I didn't know if I missed it all the way through. Okay, good, thank you. That should be star.
Yes, comparing between the controllability one we did and the observability one, this one has an x0 at the end, x naught at the end, and the one previously.
Yeah, it doesn't really matter what you call it. It's just a vector in Rn. I called it x0 here because I'm actually, typically we're operating on a state which is representing the initial state. In the case of the controllability Grammian, I was just choosing a vector x in my Rn. Yeah, and in fact, let's remove the x0 here. Let's actually just call it x, so we can be just the same as the previous. Because it really now, we should think of this just as a map from Rn to Rn. Okay, so this matrix is always positive semi-definite, PSD. It's always symmetric, but when it is positive definite, the system is controllable. And just like for the controllability case, you may be, this matrix may have rank less than n for a smaller time interval, and then as you accumulate, as you keep going over more time, it could get to have rank n. So you could have a system which is not observable over a smaller time interval, but observable over a longer time interval. And what's the intuition there? What's observability testing? It's testing, if you have enough information about the system from the output, how the output is behaving over time. As soon as you've got enough information, you've identified your initial state, and then as you go for further time, you're still going to be observable. So if you're observable over a shorter time interval, you're going to be observable over a longer time interval, which contains that time interval that you started with. Question?
At least the analog you stated for controllability, where it might be controllable for only part of the interval, and not the other fraction. I think this only holds when the controllable part of the interval includes the end. Because
No, that's what I meant here. So when I say that time interval here, that's included in that time interval. So let's actually,
oh, okay.
Yeah, so sorry, this was unclear. Let me go back to this point here. That's a very important point. That what we're meaning here is that if we start off, let's look at this time interval, t0 to t1. If the system is controllable over t0 to t1, it's controllable over any subinterval of that. I mean, any subinterval starting at t0 and going up to some time t1 prime, which is less than t1. So by subintervals, I mean you have to start at that same time interval. You can't kind of start a little bit later because maybe you achieved controllability because of what was happening at the initial time. So if it's controllable over the longer time interval, then it's controllable over a shorter time interval, t0 to t1 prime. So that's what this meant.
That's the opposite.
Oh, sorry,
of
what I'm
you
saying
said.
is the opposite. Yeah. Okay, let's write it down. So remark. Okay, let's be clear. Remark. Controllability on t0 to t1 prime implies controllability on t0 to t1 where t1 is greater than or equal to t1 prime. However, controllability on t0 to t1 does not necessarily imply controllability on t0 to t1 prime, where t1 prime is less than t1. Okay, so that's how it's structured.
And this also holds true if like the starting time of the larger interval is like before t0 as well. If like the second interval is like t0 prime.
So now we want to go here. T0 prime. So suppose you had controllability on this time interval from t0 to t1 prime. Is it controllable from t0 prime to t1? Yes, it is. So if it's controllable on that subinterval, and the way you would show that is kind of what we were saying before. If it's controllable on that time interval, then what you have to do is make sure that you can, okay, so if it's controllable on this time interval, it means that you can go from any initial state at time t0 to any final state at t1 prime. So you can do that. Now, I want to actually go from any initial state at t0 prime to any final state at time t1. So the easiest way to think about it, or at least I find intuitively, is so you have an input. You know by the fact that it's controllable over that time interval that you have an input, let's call it u star of tau, which takes you from the desired x0 to the desired x1 prime, say. Okay, so now what you have to do is just turn off the input. You have to choose an initial state here such that if you just drift, you get to the desired starting, you choose your input here. So you have to design this input so that if you had 0 input over this time interval and 0 input over that time interval, you will still get to where you wanted to start from here to where you wanted to start from here. or where you want it to end. And you do that by using the fact that you have complete controllability over this time interval, and you can basically turn off the input here and turn off the input here and set it up so that you know, if you're just looking at zero input and you drift, you get to the place you need to be here so that you can get to the place you need to be here so that if you drift, you get to the right ending state here.
I think the first implication written after remark is not true. Because suppose from T0 to T1 prime, your system is completely controllable as you would like. But after T1 prime, both A and B go to 0. Then you can
Fine.
no longer steer T1 to any vector.
Yeah, but that's fine. So if your control, it's correct. This, what we've written here is correct. Because if it's controllable on this time interval, let's just forget about that starting earlier for now and go straight to your question. It means you can get from any initial state to any final state here. But you want some different final state, or you want some, say you want to be at some final state at time t1. Then just use the input that you have control over to get to the state here, which when you turn off that input, the system will just drift to the state you want here.
What if the system always drifts to 0 by T1 because it's time varying?
But
It depends on what the initial state is here. So set up, the fact that it's controllable means you can get it exactly where you need here so that it's not always going to drift to 0. It depends on the initial state. So get your initial state here so that it will drift to the right place here. By drift, we're just using a term that means 0 input.
So what if both A and B turn to 0 at T1 prime?
That's both A and B turn to 0.
Right, because it's time varying.
That's still fine. So what happens then is you have to, so what's going to happen between, how will the system move between T1 time and, yeah? Yeah, so controllability over the shorter time interval implies controllability over the longer time interval. But the important thing is the reverse is not necessarily true.
Is there some notion of a minimal time interval over which your system is controllable? Because it seems like the time response for circuits and stuff, I think, correspond to those.
Yeah, I mean, in time varying systems, it's direct, right? There is going to be, and it's just determined by building up enough time or using enough time so you get full rank with this integral. But for time invariant systems, if you're controllable over some epsilon in time, you're controllable over the whole in time, because we allow this, because this is a vector space. So if you have an input that steers you, you know, you can just scale it up, right? So that's why I say it's sort of unrealistic, and I think that was the root of the question earlier about putting some limits on the input and still testing controllability. Yeah, so these are all really good questions, really good intuitive questions.
Could you design a system where the time, minimal time to achieve controllability is arbitrarily large depending on some scaling factor?
No, I mean, controllability means that there's a finite, I mean, by writing that, it means that these times have to be finite.
Yeah.
You can't make that arbitrarily, I mean, you can
Well,
make it large but finite.
Yeah.
And you may have that. You may have a system where it takes a long time to achieve complete controllability, or you may never achieve complete controllability, because you never, no matter how big you make T1, you may never get full rank. So that's it's called an uncontrollable system. But some subset of the state space may be controllable there. So let's go to the LTI case. All right, so we've got these tests. These tests are based on matrix rank tests, which are on basically these Grammians, which are integrals of the state transition matrix, linear time varying systems. We already know those are typically hard to compute. When it becomes easy to compute is when we have time invariant systems, because these tests simplify to much easier tests on the A and B matrices for controllability and the A and C matrices for observability. Okay, so let's now go to, so we've got these maps, we've got these matrices formed from these maps. We know We know about that very useful lemma. We've got that in our minds. We've got, you know, the way we turned surjectivity and injectivity to two matrix rank tests. So now we can go on and we can look at the time invariant case. So we're going to start with controllability, and then we'll end with observability. But observability will really just be, you know, the algorithms are going to be the same as those for controllability, except they'll be what we call the dual. So the kind of techniques that we'll use are exactly the same. So LTI case for controllability and observability. Okay, so we say, so here's the theorem. And I'm just going to write it the way we did for the time varying case. The system, actually let's do controllability to begin with. The system described by the matrices A, B, there may be a C and D, but it doesn't matter for controllability, is completely controllable on some interval 0 to delta. So you already see the difference. Without loss of generality, we're going to start at 0, and we're going to go up to some delta. Delta is arbitrary, it's just greater than 0. Or it could be less than 0, it doesn't matter. It's just a time interval. So that's statement A. Statement B is, that's equivalent to saying that the rank, actually let's put the equivalence outside B, equivalent to statement B, which says that the rank of this matrix, which is B, I'm going to form a matrix by its columns. The first ni columns are B. The next ni columns are the matrix product AB, and so on, A squared B up to A to the n minus 1B. That rank has n. All right, this is a system in Rn. Okay, so that's a matrix. This is it's got n rows, and the number of columns is ni times n. Okay, so it's an n by nin dimensional matrix. It's a short, fat matrix. Because in general, it could be a multi-input system. Okay, so I've got packages of ni columns here, and I have n of those. And that's equivalent to the following. So these are all tests for controllability. The third is that the rank of this matrix, Si minus AB, okay, so I'm going to put these lines here. We've used this before just to indicate there's a partitioning. Okay, so that those lines just mean here's my first set of columns, here's my second set of columns, but the matrix is the whole thing. And I'll do the same thing here. This is an n by n matrix. We've seen that before, Si minus A. S is just a complex number, so S is a complex number. And then I'm appending on an n by ni dimensional matrix. Okay, so this matrix here, I have n rows, and I have n plus ni columns. So it's an n by n plus ni dimensional matrix. Okay, and that has to have rank n for all s in the complex plane. All right, so immediately you see that simpler, right? Those are just matrix rank tests. Easy to, as soon as you know A and B, you can compute this. This is probably the most popular one that's been used, that people use. They just eyeball the system and they compute that matrix. They compute the rank of that matrix. Okay, so we're asking if this matrix that has n rows and ni by n columns has rank n. So if there's n linearly independent columns out of all of that. You might sort of guess, the more inputs I have, the easier I have to achieve controllability, right? Because you have just more columns to test, and that's generally true. Okay, so we usually call this matrix here the controllability matrix. It's not the controllability Grammian, but it's related to the controllability Grammian. That's called the controllability matrix for an LTI system. Controllability matrix, we call it Q, or C. So I think I've actually used both script C or Q, or the kind of notation you'll see for that. And this test is actually a nice one. It's called the PBH test. And the P is for Popov. B is for Belovich, and H is for Hautus. Hautus. Who came up with this test? And one thing to note about the PBH test is that this matrix here is an n by n matrix. For what values of S does this matrix lose rank? Eigenvalues, good. It only loses rank, by definition of an eigenvalue, right? This matrix only loses rank when S is an eigenvalue of the matrix A. It's always rank n for any other value of S. So we can immediately change this to for all S in the spectrum of A, because otherwise this always has rank n just from Si minus A without even putting B there if S is not an eigenvalue of A. So we do that because Si minus A only loses rank from n if S is an eigenvalue of A. So you basically have to check that this has rank n, that kind of B makes up for that loss in rank when S is an eigenvalue of A. Okay, so now we want to prove this. And we'll do some of these proofs. So they're all equivalent. So completely controllable is equivalent to this test on the controllability matrix is equivalent to the PBH test. So let's prove, we'll choose a few to prove. Let's start with A implies B.
Nice question.
Yeah.
This is supposed to be S, not in, because it is.
Sorry, for all S not in.
No, it's rank N, it's not in there. Yes.
Yeah, no, that should be S in rank of it. Yeah, no, but what we had was fine, right? The only place that it's going to lose rank is on an eigenvalue of A. Because what I'm saying in the notes is that this matrix always has rank n if S is not an eigenvalue of A. Okay, so let's go from A to B. So completely controllable. Okay, well we know what it means for a system to be completely controllable. We have the Grammian test. So let's go back and write what the Grammian is. Let's just choose some T0 to T1 and write it for this time invariant system. All right, so we have the controllability Grammian over there. So phi of T1 tau, we know what that is. It's e to the A T1 minus tau. B is time invariant, so that's just B star, and then e to the A star T1 minus tau.
So the demo should be from T0 to T1.
T0 to T1, thank you. D tau. Okay, that just comes from the general test for time varying systems, of which a time invariant system is obviously one. And then we can just do a change of, I'm just going to change the variable of integration. So I'm going to define some tau bar, which is equal to T1 minus tau. And I'm going to rewrite that test, or that integral, as the integral from 0 up to T1 minus T0 of e to the A tau bar B star e to the A star tau bar B tau bar. Okay, so it's simpler. And then I'm just going to define delta to be T1 minus T0. Okay, so we want to prove that, so that's what it means. Okay, so for this, if the system is completely controllable, it means that this matrix has rank n. Now we're trying to prove that this matrix has rank n. That's an easier test than doing this, right? So let's show why that implies B. And let's show it by assuming that B does, that matrix in B, the controllability matrix, does not have rank n, and let's derive a contradiction. Okay, so assume B is false. that means that the controllability matrix loses rank. And so another way to say that is that there exists some vector which is in the null space, which is non-zero, which is in the left null space of that matrix. Okay, so I can write that as V transpose V A B A squared B up to A to the n minus 1. V is equal to 0, and that's the n times ni dimensional 0, and it's 0 transpose. And that V is not equal to 0. So there's some non-zero vector which is in the left null space of that matrix, if that matrix has rank less than n. Alright, so check why that's true. Check as an exercise. But now from this I can break this down, right? That means that V transpose B is equal to 0, and that's going to be this ni dimensional 0. V transpose AB is equal to 0, all the way up to, do it for each of those column sets, A to the n minus 1B is equal to 0. So from that, from Cayley-Hamilton, we know that that tells us that V transpose, all those together, any analytic function of A times B is equal to 0. Okay, because I've got A squared up to A to the n minus 1, and so that tells me that specifically V transpose E to the A T B is equal to the 0 vector. Okay, so if we have that, then we have that V transpose WC V is equal to 0, which contradicts the positive definiteness of WC. Okay.
So what we did here was, over here, we're trying to, we wanted to show that that thing has rank of n, but then it's not so easy to do, so we instead.
No, but over here we wrote down what the Grammian was for the, so we took our general definition of the Grammian for time-varying systems, and we specialized it for the time-invariant system. And then we said, okay, let's hold that on the board over there. Now let's assume that the thing we're trying to prove is false and derive a contradiction. So I'm going to show that A and not B is a contradiction. And so if I assume that B is false, directly from that I get a statement like this. And directly from that I can bring B into the columns and I get these are all 0. Which leads me to this being 0. But this piece here is just this piece here. Okay. So if I know that this is equal to 0, then if I look at, instead of E to the A transpose B, if I plug in WC in there, take the expression for WC, plug it in there, bring the V transpose in, I just get that's equal to 0. And so that gives me the contradiction with WC being full rank. So this contradicts. Full rank. I'm going to do one more of those directions, and then I'm going to leave the other directions as an exercise. So I think I'll prove which one should I do? Let's do one that's kind of different. So some of these are the same. So I'm going to now prove the last one. Actually, I'm going to prove that, so to do this proof properly, we have to prove that A implies B, B implies A, then we can prove B implies C and C implies B. You don't have to do everything, because once you've done some subset of them, you have all the double implies. And we have enough there in the notes, but I'm going to at least start and show you the outline for C implies B. And then we'll end on that. All right, so let's do that one. Let's erase this and just start that proof. And And then I'll give you an exercise on the homework where you can do the other proofs. And they'll be in the notes, so you'll have some guidance. So we want to prove now that proof of C implies B. All right, so we've done this proof, this to this. We want to prove this implies this. Okay, so I'm going to prove that by saying C, I'm going to sort of do what I did before. C and not B is a contradiction. So if B is not true, so not B, so we've already seen what it means for B to be not true, but I'm going to write it in a different way here. So this matrix, which we call Q, which is the controllability matrix, that's, that matrix, so I can write it as, if I look at this, actually, let's write it, let's not call it Q, because I called that the matrix. Let's say the span of the columns B, A, B, up to A to the n minus 1b. So the span of the columns of the controllability matrix is not Rn. So it's some subset which is not equal to Rn. Okay, I've assumed not B, so I'm assuming that this doesn't have rank n, it's got rank less than n. N is the maximum rank it can have, right? Because that's the number of rows of this matrix. And I'm going to call that, that span, well, let's just call it Q, as the span of the columns of the controllability matrix. And we also see, by our definition of A invariance, we see that Q is an A invariant subspace, which we proved is one of the exercises when we were talking about subspaces, an A invariant subspace of Rn, and we also know that it contains the range of B, because in fact, B is, it's contained in that span. So that's a subset of Q. So we don't make up the whole of Rn by looking at the span of those columns. So I'm going to choose V1. So I'm going to let V1 be any subspace which completes up to Rn, which completes Rn with Q. And what I mean by that is that if I look at Q and I take its direct sum with V1, I get Rn. Now, this is something that we've seen before.